So the topic of our seminar for today, the title we've given it is we're going to focus on outdoor emission inventories, as that's where our area of expertise lies, and the role that they have in source apportionment and also policy formation. So this is just a quick sort of overview of what the seminar will be. So we'll give a very brief introduction to Aether and the company. We'll go into what is an emission inventory and why we do it, with a focus obviously on air pollution. We'll briefly touch on international reporting and legislation, and then we'll talk about different sorts of tools that we have to use to support the assessing of air quality. So first of all, emission inventories, emission maps, and then how that feeds into dispersion modeling. And finally, we're going to briefly touch on the importance of emission inventories in relation to policy formation, and how the two are linked and why it's so important that we do these emission inventories. As Malcolm said, if you have any questions, please feel free to put them in the Q&A and we'll try to answer them either during or we'll save some time at the end of the session also. So just briefly, Aether, so we're a consultancy which was founded in 2008. We are based in Oxford, but obviously we have very much a hybrid working environment now, and we also have an office in Madrid. We're quite a small company, so we're about 26 of us, and we basically specialize in emission inventories and also the analysis of broader environmental data. So under emission inventories, we look at both greenhouse gases and also air pollution. We have under this bracket, we also have a wide range of sort of projects we do. So we look into industrial reporting, we look at MRV capacity building. So MRV is the monitoring, reporting and verification. We work alongside property developers with their air quality assessments, international organizations such as the EU and the EEA. We look into the wider impacts of climate change and air pollution. And we also have seen a huge growth in work with cities and local authorities. And that's obviously been brought on by all the climate action plans and net zero. So that's sort of a bit of a also stop tour. And then obviously we work for national governments as well. So both Annex 1 and non-Annex 1 countries. So first of all, what is an inventory and why do we do it? So this is a very broad sort of definition. So it's an estimate of all the emissions and removals, so either of greenhouse gases, or in this case of air pollutants from, quite importantly, given sources or sinks in the context of GHGs from a defined region in a specific period of time. And what's important to note that the region obviously doesn't have to just be national. So obviously we can do a national inventory on air pollution for the UK, but we can also do sort of more regional and local. So we could do an emission inventory for the city of Leeds, for example. The time resolution sort of looks at the coverage. So you're trying to calculate emissions for which years. So typically we try to do from 1990 to 2019. And it's 2019 because it's X minus 2 years. So obviously we're in 2021 right now. And as it takes time to collect the data, perform quality checks and all that, it takes about 2 years from when we've got all the data complete. So that's why it's always -2. And that would be a sort of a whole time series, but obviously you can do a shorter time resolution if you wanted to. There are defined sources, and typically in an inventory, we like to cover and include all the sources, so from different sectors. And then there will be defined sort of pollutants that we look into. So greenhouse gases, you've got the sort of 6 key greenhouse gases under the Kyoto Protocol. And then for the air pollutants, you have your obvious ones like NOx and SOx, particulate matter, VOCs, and then also under air pollutants, we include heavy metals and POPs as well. So why do we do it? a number of reasons. So first of all, countries like to calculate their emissions in order to check if they're being compliant with legislation. So for example, if they've got commitments and reduction commitments that they need to meet, it's important for them to figure out sort of if they're going to meet them, and also under, UNFCCC rules or the CLR TAP, which I'll go into in a bit in the next slide. There are requirements where basically a country has to report normally annually. It can also be really helpful to develop policy strategies. So once you know what your emissions are and what the biggest sources are, then you can help to, it helps to tailor what your policy should be. You want to target the largest sources, and this can help to form policy strategies and action plans. It can also be a good way of tracking how well a policy is doing. So if you've implemented a policy in the past and you can see that there's a reduction in emissions following that, you can try and see, is there a correlation? Is the reduction in those emissions due to a successful policy? And finally, it's obviously very important for research and public information. So in the context of air pollution, one of the main interests is its impact on health. So it can help with health impact studies, dispersion modeling studies, and also environmental impact assessments. So why do we do it? So obviously the World Health Organization has guidelines, which I'm sure you're very aware of, and they've recently actually just been updated. So the guidance is that pollution levels have to be below a certain level of concentration. So for PM2.5, the annual average has to be under 5 micrograms per cubic meter. And for NOx, it's under 10. And it's estimated, in 2019, they estimated actually that 99% of the population was living in places where the World Health Organization deemed it actually that these air quality levels were not met. So the CLR TAP, so this is the UN's convention, and CLR TAP stands for the Convention on Long Range Transboundary Air Pollution. And it's essentially a convention under the UN, with many countries have ratified to essentially pledge that they will reach certain reduction commitments. The UK is one of them. So under that convention, they have to report annually on those 5 pollutants. And within that convention, there's a protocol called the Gothenburg Protocol, which is what sets these national reduction commitments. So that's sort of why the UK has to calculate their emissions every year, because they obviously have to report under the Gothenburg Protocol to this convention. And finally, also interestingly, there's a growing emphasis from the climate change side to understand a bit more about air quality. So the UNFCCC, obviously in charge of the Paris Agreement, so reducing greenhouse gases, but they also want to recognize that there are some co-benefits which might emerge from reducing greenhouse gases. So the costs for reducing a certain greenhouse gas might be minimal, but if you add in the additional benefit coming from reducing air quality, it could actually mean that the impact is far greater. So it's really sensible to look at it in an integrated sort of holistic way. Obviously, it's important to note that there's not always co-benefits. Sometimes there can be negative impacts. So for example, in some climate action plans, the increased use of sort of biomass and wood chips, for example, to reduce for low carbon strategies could actually lead to an increase in air quality. So there's always an interaction to consider. So that brings us nicely onto this graph or Venn diagram, and that sort of shows the overlap. So on the left, you've got the air pollutants that I mentioned alongside some other ones. Sort of the key ones are the 5 at the top. And then you've got the interplay between air pollution and greenhouse gases and what we call short-lived climate pollutants. And these are substances with quite a short lifetime in the atmosphere compared to CO2, and they're assumed to have a short effect on the climate system, but they do lead to warming. So the two big ones are, in the context of air pollutants, you have black carbon, or BC, and this is particulate matter which can settle on the surface, and it sort of affects how much light is reflected. And there's an increasing interest in particulate matter, or black carbon, and it's largely created as a result of incomplete combustion of fossil fuels, biofuels, and biomass. And then you have ozone. So some of the gases emitted are ozone precursors, where they have sort of a chemical reaction in the atmosphere where they form ozone. So ozone itself isn't emitted. And so pollutants like NOx, VOCs, and methane and carbon monoxide can lead to the formation of ozone. So it's always quite important to consider that there is that interaction between air quality and greenhouse gases. Other sectors that also benefit from integration of both air pollution and greenhouse gases. So for example, agriculture, in the nitrogen system for greenhouse gases, we're only obviously want to consider N2O, but under air pollution, you'd also want to consider NOx and ammonia, and make sure that there's no sort of double counting in the nitrogen cycle. Just briefly, so traditionally emission inventories, we try and represent all the sources, but at the moment there's very much been little to no attention given to specifically reporting indoor only or outdoor only sources. Getting that separation can be difficult. However, there is increased interest, especially on the indoor air quality, linking to health. But in order to do this, we'd have to improve the inventories to specifically resolve indoor and outdoor sources. And I've put here DUCOMS in brackets, which is a project funded by the Met Office, which is looking to build a tool to actually look at this interaction between indoor and outdoor air pollution. And hopefully that tool will be for public use in the next year or two. It also requires poorly estimated indoor sources to be improved, because at the moment, the estimation methods that we have aren't quite good enough. Okay, so next we'll go on to tools to support assessing air quality. So obviously I've already spoken about emission inventories. So they're very powerful due to the information they provide. So they allow us to estimate the amount of pollutant by source, and that links to the source apportionment. And it also shows us how emissions have changed over time. And this can then feed into the basis of projections. So if you've got your baseline, you can then use that to project what you think your emissions are going to be. And those projections can then also help to lead to policy formation. If you're projecting that emissions, for example, from industry are not reducing at the rate you would want, but are stagnating, you can try and bring in targeted policies specifically to reduce emissions from that sector. And then obviously they can help to track any sort of success stories. So in the diagram here, you've got a case study in the UK. So we've got SO2 emissions in kilotons. And you could see that with the NECD. So the NECD is the National Emissions Ceiling Directive, which is the sort of EU equivalent of the CLR TAP. So it's a reporting requirement under the EU that the UK used to ratify. So they would have to, under the NECD, they would have emission reduction commitments that they would have to come under. And you can see that they successfully reached these commitments sort of around 2008 time. So that's sort of a success story. And we can see that from an emission inventory. So one of the sort of larger differences with greenhouse gases is that with air pollution, we're not just wanting to know how much is being emitted, but also where. So we're interested to know where the emissions, so from where are the sources from, specifically if they're sort of near people. Emissions from sources that are far more remote probably don't matter quite as much. It's more linked to sort of human health. So that's why emission maps can be really, really useful. And these use, they sort of visually demonstrate and localize your emissions. So for example, here we've got one for Leeds that my colleague Luke brought up. So this is black carbon. And the resolution is, so each square represents 1 kilometer by 1 kilometer. And as you can see, so the unit is tons. So as you can see, the sort of red regions indicates where areas in Leeds where black carbon emissions are sort of higher. And then you can kind of try and link that with things like roads. So Luke helpfully put with the sort of little pinpoints where some of the hotspots were. And we can see a correlation in some areas where the red, so the areas with high emissions, correlate with where there's sort of major roads, or in the bottom right-hand side, there's a textile manufacturing called Pittards, and that also correlates to sort of where the color is red. So that can be a really useful tool. It helps us to sort of visually show where the main sources are, so we can try and target our policies to target those specific areas. And we might want to reduce emissions, but we might also want to displace them and move them to places where there are less people around. And the graph on the right is sort of UK based and similar 1 kilometer grid squares in tons. So this is for 2002, and it's emissions from NOx. So as you would expect, in sort of London, central London area, very red, so indicating high emissions of NOx in that region.
We should just add very quickly, that this map here, it's showing emissions at a by-source level. So this is just as it's being emitted, when it's not really capturing what happens to it when it's released to the atmosphere. So when you see those sort of red squares there, that's just a hotspot of where black carbon is produced. Where it ends up, it might be blown away downstream somewhere, or it might be captured between high-rise buildings, something like that. Yeah, so these maps are just by source. I just wanted to quickly add that.
Thanks, Luke. And that nicely leads on to the concept of dispersion modeling. So as Luke mentioned, once the pollutant is emitted, then there was a process, an atmospheric process of how the pollutant will get dispersed from the source. And that can consider things like meteorological inputs, so like wind. And a dispersion model takes the emissions and helps to convert it into a concentration map, where you can sort of predict what the concentrations will be at selected downwind receptor locations. So for example, in this case, this is a road in Oxford, and we're in the units now is micrograms per cubic meter, which is concentration. And you can see where the concentration of NO2 along this road is in Oxford in 2018. And what you could do is, in order to validate the outputs of your dispersion model, you can then use things like diffusion tubes to sort of accurately see if the concentrations maps that you've calculated are indeed correct. So the dispersion modeling sort of helps to calculate the relationship between emissions and concentrations. And as we see from the World Health Organization guidelines, they're very much focused on concentrations, as that's what will impact on human health. So emissions are sort of what we can control, but the concentration is what we are aiming to reduce, so we can reach those guidelines and targets. Okay, and then briefly, So we've briefly touched upon this. So how do they feed into policy? So once you've created your inventory and you've understood what the main sector contributors are, then you can start to sort of develop a policy strategy, implement those policies, and then you want to track your progress. So this is a time series. So it's an example of a time series. This is just dummy data, so it doesn't represent any sorts of specific country or city, or it's just purposes of demonstration. So this time series is 2000 to 2020, and you can see the different, the color coding obviously by sector. So in this instance, emissions from residential, that's the largest source. And once you've got your baseline year, you can estimate emissions in future years. So in this graph, we can see that they've projected their emissions to 2030, but you can go beyond, so 2040, 2050. And in projections, you have the concept, which is with measures. And this essentially is, if we were to go on as we are, with the current measures we have in place, this is what our projections are likely to be. So generally, we would expect emissions hopefully to reduce as cars get cleaner, appliances at homes get better. However, there is more we want to do. So in this example, with measures, or you can also call it with existing measures, is the dark orange line. But if we wanted to bring in further measures, policies and measures, because we see we're not going to reach our reduction emission commitments, then we want to bring in new, we can bring in new additional measures, and then that would be our WAM scenario, which is the WAM scenario, the faded orange dotted line. And then that can help us then to identify, will we meet our commitments? If we're still not meeting our reduction commitments, then we need to think even further, think even bolder. And as we've got as we've established the relationship between the emissions and concentrations, you know, we know now if we reduce emissions in this instance, and you can then do your dispersion modeling, you can see how that will then impact on the concentrations. And if you're going to reach your concentration commitments under the WHO. Just finally then, so cost benefit analysis can be very useful as well. So if you wanted to add, so in policy making, obviously, policymakers are interested in knowing how much a policy and measure might cost. So by adding more information on cost, that allows us to build a group of policies, which then develops into a strategy. And the priority and strategy should be to reduce concentrations where the people are. But as I've previously said, that could simply be displacing the emissions if need the concentration to elsewhere, if needs be, where there are less people. And then obviously it's useful for checking progress and policy effectiveness. In due course, the emission inventory shows whether policies are having the predicted required impact on emissions, and that the concentration measurements are reducing as we would expect. But obviously it requires political will and support. And that's everything from me. Thank you. Are there any questions?
That's great, Justine. Thank you. And I've just typed into the chat, inviting people to add their questions. But thank you very much indeed. That's been really helpful in getting our heads into the inventory space. So any questions from anyone before I kick off? Okay, so I'll start. Oh, Kath, sorry there.
Sorry, I did it wrong. I was supposed to type, wasn't I? Yeah, thank you, Justine and Luke, for a really, really interesting talk there. So, I mean, it looks like you've got data at quite granular scale there. You've got it at sort of individual road levels and places for those emission outputs. I'm thinking about how, you know, people like us who tend to think about modelling city scales and building scales could possibly use some of this data to get sort of realistic values to input into models that we could use then to look at risks in buildings from those data.
Okay. Yeah, well, maybe the resolution on those graphs is a little misleading because there are, with every modelling approach, sort of quite loads of assumptions.
I realise it. Yeah, I know. I realise it probably is a bit not quite that. But it's still quite a resolution that was. It's still a lot finer than I was expecting it to.
Yeah. Well, in cities at least, the dominant source in the outdoor space would definitely be just cars just travelling up the trunk roads and stuff, which is probably why we saw lots of those red squares on that Leeds map align quite heavily with where the major hotspots would be. Yeah. And I know the resolution for that is based largely on sort of traffic count data that DFT collect. But then we have to make broad assumptions about what because when we're traveling across roads, you know, sometimes you sort of trigger these sort of two parallel black lines, which that's essentially counting, you know, cars traveling in and out. They have to make assumptions about which vehicle has just passed those two things, whether it meets a different Euro standard, which is, you know, if it's one of the older, more polluting times, whether it's younger, that kind of thing. But certainly in cities, at least, you could harness that data. So a good source for that would be, because the NAI do that sort of modelling on, I think, that kilometre resolution. And if you do the data, you can just ask, and I think they're bound to give it to you. I think they're required to. But yeah, that's the sort of, it is available at that sort of level, which would be helpful for your modelling, I'm sure.
Can I ask another question as well? Sorry, Marco. Is there any, you've got quite a lot of sources there. Do you get any sources from buildings? Do they contribute, and how do you count them?
From
as in from building, from their heating systems or things like that?
Yes.
Or smoke from
yeah, absolutely. Yeah, they're all included in the sort of, well, any sort of national inventory, especially as people are starting burning more wood. They're becoming increasing contributors in the urban space. So yeah, that would all be incorporated, although the assumptions for that on the sort of resolve level are much more broad, because we don't actually know who's got a wood burner. So
I guess, you know, the sort of volume of sales of wood burners and the
and then sort of density of population, so you make some broadish assumptions based on that. Yeah,
cool, thank you.
That's right.
Your question, Kath. Thank you, Luke. Okay, we've got a couple of questions in the chat. We got the first one from Hugh Woodward. So yeah, thank you, Justine, for the interesting talk. Do you know how your national emission estimates compared to the NAEI? I'm particularly interested in ammonia from agriculture, which is an increasingly important but uncertain source. So ammonia. They are one and the same. So Aether contributes to the national inventory itself. So the bits that we work on are sort of the devolved administration inventories, which separates essentially the UK national inventory data into England, Wales, Scotland, Northern Ireland. So yeah, they're the one and the same, our estimates and theirs, because they are we estimate them essentially. Okay, thank you, and we'll move on to the next one from Bryony, which is asking where the NO2 data comes from. Is it from the Copernicus Sentinel satellite?
In terms of the emissions inventory estimates, or do you mean the eventual concentrations? Because I can answer both. The inventory estimates, there's a sort of, it doesn't come from Copernicus, because Copernicus would measure concentrations downstream rather than estimating emissions at the source. So this is the point I was trying to make earlier when I interrupted Justine quite rudely. The easiest way of doing an emissions inventory is at a by source level. So we sort of, if you can estimate your emissions coming from an engine as it's burning fuel, for example, in the car, it's easy to measure the emissions at the actual tailpipe rather than them being distributed downstream. So those NO2 estimates that we've got are based on sort of that level. We're applying the knowledge from measurement studies done on tailpipes, and then developing essentially emission factors that we can apply to the whole of the road transport fleet based on that, rather than using Copernicus data. But the NAI is meant to be validated against measurements. I think the Met Office do those measurements. I don't know if they come via Copernicus. If that answers the question, I don't know if it particularly does.
Thanks very much, Luke. We'll assume for now it does. I'll invite Brian to come back if she's got any follow-up points. So a question from Ellie McCormack. Great talk, Justine, thank you. You mentioned diffusion tubes to measure NO2, which take a long time to record the concentration. Would higher time resolution measurements be useful in terms of policy?
Yes. So you do get other sort of measurement things, and then they would be used to help with your calibration of your dispersion modeling, if you like, and help with making sure because the way we use dispersion modeling is to sort of to figure out what sources are contributing to whatever you're picking up in your diffusion tube, or if you're using a monitor which does it in real time. And then I've lost my trail of thought now. Essentially, using real-time monitors would help with that calibration process, because we can. I mean, there's some are available, but I don't know your opinions on the accuracy of them. But when I was in a previous life, I was trying to install some around London, because I was worried about the ships running up and down the Thames, and there was a great debate whether what we were picking up on the sensors themselves was actually a decent reading or something else. But yeah, in principle, if we can get high quality real-time measurement data, that would be much better.
Okay, thank you. While we're waiting for any more questions and comments, I'd like to ask about the emissions maps, which are always very interesting because they're always very colourful. If emissions were to be suddenly turned off, say in the event of a global pandemic, how quickly do those red colours start to turn blue? I'm an indoor air modeler as opposed to dispersion modeler, so I don't have an immediate appreciation for how quickly pollution in the air disperses, and of course it will depend on weather conditions, etc. But in the event of a global pandemic, no traffic on the roads, or very, very little traffic on the roads, how quickly, in terms of hours, days, weeks, would it be for us to turn the M1 into something like Western Scotland?
Yeah, well, the answer means it's a cop-out, the answer, but the answer is it depends on the pollutant, really, because some would remove themselves by the sort of timescale that it remains in the atmosphere. It wouldn't be too lengthy, but for others, the sort of photochemical reaction pathways can last for days, weeks. So if we were to essentially disappear, it would probably clean up within a week and a half, 2 weeks.
Okay,
I would guess. But then in the case of a pandemic, we're sort of switching where we're using our energy rather than.
Yeah, indeed. No, thank you. That's a helpful response. Matt Hort, you mentioned emissions estimates based on bottom-up approaches, i.e. exhaust measurements, engineering studies. For greenhouse gas work, there is also an activity based on top-down, i.e. where concentrations are used and models used to estimate the emissions needed to result in those concentrations. For air quality species, this is potentially much more complicated, but I would be interested in any thoughts, comments on this approach for air quality species.
So I'm just trying to follow the question. Where concentrations are used and models are used to estimate. I don't know. I'd have to go back and think about that one, actually, I think.
It sounded like a tricky question to me.
Yeah, I'm reading it and so I mean, I'm reading the words but not soaking it in. I'll come back to me on that one.
Yeah, sure. Okay. I'll just ask my question about black carbon, Justine, that you mentioned, and black carbon absorbs sunlight. How high in the atmosphere do these particles rise generally?
For black carbon, it's all done on the basis of sort of incomplete combustion. It's the way we calculate it for emissions inventories. It's because the research for black carbon is fairly new, to be honest.
Okay.
But it's all done on the basis of particulate matter. So things that produce particulate matter, we tend to assume would produce black carbon, and the things that are liable to produce more black carbon, other things are any sort of engine or boiler or anything that would be liable to have incomplete combustion. So that might be more solid fuels rather than gaseous fuels, for example. So if you're burning wood or coal, because of the sort of heterogeneous chemical structure of those materials, the combustion conditions within whatever boiler you're using, it won't burn everything in a sort of consistent way. And if you're not at a suitable temperature, then you're liable to produce particles which haven't burned properly, and it's just a sort of black carbon emission that comes out the engine.
Yeah, I mean, it's an important point for us actually on the Breathing City Future Urban Ventilation Network, because, as I said, I'm an indoor airflow modeler, but I'm keen to find out what's happening at the boundary of my building. So where are the pollutants? What's the density of the pollutants just outside of the building? How dependent is that on urban planning, on wind speed and wind direction and that kind of thing? And I think there's a lot us indoor airflow modelers can learn from from teams like yourself and inventories like the ones we've been talking about. So it's really a comment more than a question. Yeah. Okay.
I've read Matt's question now, which is why I was delaying to respond to you. I was like, I think I finally get it. And my answer is I'm not sure of whether that sort of approach is being used for air quality species. But you're right, it would be a bit more complicated. But I'll take that away with me and get back in touch with you, Matt.
Thanks,
if I find anything.
Yeah. Okay, any more questions before I wrap up? Any more questions? Okay then. So all that remains is for me to thank Justine and Luke. We all know that these inventories exist, but it's been great to actually see the people behind some of these inventories and for you to unpack them for us, Justine. Thank you very much. I thought you gave an excellent presentation, and you made it very visual, very accessible, and that's borne out by the comments in the chat. So thank you very much indeed for that. Our next seminar is on Tuesday, the 30th of November, from 12 to 1 p.m. GMT, and that will be given by Paul Agnew, who's the manager of the air quality and composition team at the Met Office, and he'll be talking about an overview of Met Office air quality modelling developments. We will let you know more details about that and a reminder nearer the time. But before we close, please can I encourage you to unmute and show your appreciation to Justine for this lunchtime seminar. Thank you.
Thank you. And thank you, Luke, as well, for answering questions. Thank you, Malcolm, for having us, and Helen as well.
Absolute pleasure. Thank you very much.